So today we're going to be discussing about vectors, scalars, addition and subtraction of vectors, and other operations you can act on vectors. So what exactly is a vector? So a vector is a quantity with magnitude and direction. So we're also going to be defining the scalar. So a scalar is a quantity with magnitude. So vector is magnitude and direction, and scalar is magnitude. But I should mention that scalars only have magnitude, and basically vectors aren't scalars in that they don't fit that they only have magnitude, rather they have magnitude and direction. So what exactly would a vector look like in terms of normal human terms? Or well, normal terms, I'd say. So a vector would just be like 15 meters east. So the directional component is east, and the magnitudinal component is meters. And well, a scalar would just be 15 meters. So if you see a directional component, say east, west, north, away from the earth, towards your brother, or whatever, that's gonna be the directional component. And if you say 15 seconds, 1.5 light years, 500 billion megatons, that is a scalar quantity. So next, we're going to be talking about basis vectors / unit vectors, but they're pretty much the same thing. So basically, like, basis vectors can take quite a few the three main notations that people use. So first is I hat, j hat, which is just x and y respectively. And well, we also have e hat x and e hat y, which is also x and y. And we also have e hat 1 and e hat 2, which is, well, x and y respectively. So basically, these are the main. So basically, the unit vector is basically like the directional components the vectors actually have. So like if we were to say, 15 meters east again, would that just be, well, since east is in the x direction, right? X and east, and well, west, north, and south. Well, that would just be, well, 15 I hat, or 15 e hat x, or 15 e hat 1. And if I were to change that to, well, west, well, those just apply negative signs. So you can see how these unit vectors can be easily applied to real world casual terms, say east, west, north, south, because the definition of all of these unit vectors is just gonna be, well, x, y, which is just, east and west and north and south. So how can we put all of this together? So basically, well, we can write the vector in equation form, where let's say we have vector v, where this arrow is the notation, is just going to be vx, the x component of the vector, e hat x, plus vy, e hat y, or I hat, or j hat, or e hat 1, or whatever notation you use that helps you understand. But I'm just going to be using e hat sub x because I just think it's easier to understand, and that people are more familiar with Cartesian coordinates. So anyway, so we have this vector v that's equal to vx e hat x plus vy e hat y. And basically, if we wanted, like we know that we wanted that vectors have direction, which is in these unit vectors. Well, what exactly would the magnitude part of the vector be? Well, so we denote the magnitude of v by these absolute value bars. It's going to be equal to the square root of vx squared plus vy squared, and well, all of that under the square root. So how can we derive this value? So well, I think a handy picture would help. So I should mention that this is how you represent vectors on the Cartesian plane. And this, let's say this is vector v, and you can see that this length is just vy e hat y, and this length is just vx e hat x, right? Because well, if you apply the arrows, this is just all of that in the x direction, all of that in the y direction. And as you can see, if we were to take the square of, let's say we wanted to square these components. So vx e hat x squared plus vy e hat y squared, all under the square root. And as you can see, this is equal to vx squared e hat x squared plus vy e hat y squared. And this brings rise to a very important property of unit vectors, in that if you were to multiply the unit vectors of, like, say, e hat I and dotted, we'll talk about the dot product more, e hat j, that's going to be equal to this thing called the Kronecker Delta. So what is the Kronecker Delta? This is a new property we have seen in this new quantity. So basically, the Kronecker Delta, so let's say ij, is defined as, well, this is basic quantity is 1 if I equals j, and 0 if else. So like, let's say we have delta 1 and 2. Well, that's just equal to 0 because, well, I is not equal to j. What about, but delta 1, 1 is equal to 1 because, well, in this case, I equals j. It's a simple concept. So basically, if we were to take the vector squared, to just be multiplying them squared, and then just be vx squared, and see, because e hat, we know that e hat sub x is equal to e hat sub x, there'll just be 1, and the same logic applies for e hat sub y. So ey hat, not ey hat, vy squared. So thus we have been able to derive why the magnitude of the vector is equal to, well, the components squared all under the square root. Well, we have all of this terminology that's part of vectors themselves, but what would happen if we were to add it to other vectors? Like, cause you can add vectors, well, we're gonna be talking about adding / subtracting vectors. So let's say we have a vector v is equal to vx e hat x plus vy e hat y. And w, let's say we have another vector w is equal to wx e hat x plus wy e hat y. So what exactly would it be if we were to add these two vectors together? Well, you see, adding these vectors together are merely as simple as doing basic algebra, which would just be equal to substituting the values for v vector and w vector. It would just be vx e hat x plus wx e hat x plus vy e hat y plus wy e hat y. And as this is easily factorable, so factoring this, we just get e hat x times vx plus wx plus e hat y times wy plus Vy. There's also a way to visually represent it. So let's say we have, well, vector v and, well, vector w. So if we wanted to add v plus w, the graph of that would basically be the tip. So like this is vector v to tail. So, and this would just be like, let's say we have another vector, t. So so let's say this is equal to t vector. It would just be equal to t vector. So the base of this is the same, and the end point of the other vector is the same. Same logic can be applied to subtracting vectors. So like, what if we were to do v vector minus w vector? We can rub this out because we already did write that. So v vector minus w vector. So basically this would just equal to v vector plus negative w vector. And it brings up a new term, so we're scaling. So basically we're scaling. So let's say if you were to have a w vector, this would just be equal to a times the components. And yeah, pretty much multiplying it by the whole vector. So in this case, a equals -1. So negative w vector is equal to negative vx e hat x plus w, oh no, sorry, minus wx, no, not wx, oh, I'm sorry, minus wy e hat y. So if you wanted to substitute the values for negative w, this would just be equal to vx e hat x, and then negative wx e hat x plus vy e hat y minus wy e hat y. And then we could just, well, factor it again, and then we just get vx minus wx e hat x plus vy minus wy e hat y. So it's pretty much the exact same logic to be applied. So and then this would just be the new vector. And then you could also just like, let's do like adding them graphically again. So vector v is this, and then vector w is this. So v vector minus w vector, well, we know is equal to, well, let's just call a vector. So like, this would just be the exact same thing, but, well, let's say so negative w vector would just be, well, the graph would be, well, it would be the opposite, well, it'd just be the opposing direction. So applying this tip to tail, so v vector minus w vector would just be, well, what would it be? So like no, not e. I'm stumbling on my words today. So v vector, and then, well, it would be this, but, well, the opposite direction, this. So this is w vector and negative w vector. So we can just rub this out, and then you can see, and then you could draw a vector from the tip to the tail, and then this is a vector. So like basically it's just the same as the addition, but you basically just like you put this, say this is v vector, right? And we had w vector again, and let's say we could just draw it that way, and then we just like draw the exact same length, but in the opposite direction. And then we just basically put like tip to tail like we've done again. So like the base of the resultant vector is equal to the base of the v, and the tip is equal to the other vector. So yeah, really, addition and subtraction are probably the most trivial parts of understanding vectors. As long as you understand how to add the basis vectors properly, you'll be good. Yeah, that whiteboard's a bit dirty. So what if we wanted to do multiplying vectors together? So what exactly would that be? Well, what do you think? Well, there's actually two types of multiplication between vectors, which we'll talk about right now, which is the dot product and cross product. And the difference between these two that you can see clearly is that this one yields a scalar and this one yields a vector. So let's go over the dot product first because, well, it's easier to understand and it's easier to compute. And well, let's say we have this vector v again is equal to vx e hat x and yada 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 e v hat vy e hat y. And well, it's the same for w, wx e hat x plus wy e hat y. So dotting those vectors together, it would just be equal to, well, since it's a scalar, this would just be, well, since we know that it would just be equal to, well, vx e hat x plus vy e hat y dotted with wx e hat x plus wy e hat y. Well, as you can see, all of these cross terms, so this one and this one, and this one and this one, go to 0, because since they're different vectors, the Kronecker Delta makes it so that, and since x doesn't equal y, these terms will just go to 0. So, and then we could just, well, multiply, we could just multiply the other terms. This should just be equal to, since, well, the Kronecker Delta makes it so that these two, so that this multiplies to 1, this would just be, and these two multiply to 1, would just be vx wx plus vy wy. So that is the dot product of two vectors. So let's give an example. Let's say vx is equal to, well, 5, vy equals to 3, wx is equal to I, where I is equal to square root of -1, and wy is equal to 4. So, well, this formula would just tell us that the dot product between the two vectors would just be, well, vx times wx would just be 5i plus, well, vy and wy would just be 12. And as you can see, this yields a complex number because, well, anything that's in the imaginary plane is going to be considered a complex number, or rather imaginary number. But I'll just put it on a complex number because it's easier. While the dot product is a pretty easy concept to understand and derive, the cross product, on the other hand, is not as easy. So there's one way of deriving this. So what if you wanted to cross v cross w? Well, this would just be equal to, well, let's just say we have to take the determinant of the matrix. And I can see that matrices are kind of hard to deal with, and the other one is also probably going to require some prereqs. So ex, ey, and also I should also mention that, well, basically two-dimensional terms are undefined when using the cross product. So we're going to defining v as equal to vx e hat x plus vy e hat y plus vz e hat z, and the same for w. W vector is equal to wz, no, not wz, wx e hat x plus wy e hat y plus wz e hat z, and then e hat z, which is because it's basically all of these unit vectors on the top, and then I'm trying to remember, and then it would just be vx vy vz and wx wy wz. So basically taking the determinant of the matrix means that you take the determinant of vy vz wy wz times e hat x plus e hat y times vx vz wx wz plus e hat z, well, e hat z would just be vx vy wx wy, and this all just results in e hat x times vy wz minus vz wy plus e, oh wait, no, this is a minus, I'm sorry, this would be a minus sign. So minus e hat y times v. So I think I've done this wrong. I think this should be vx wz minus wx vz, or is it? Whatever, just keep it like this for now. And no, this is, I'll just keep it on the order of vz wx because simplicity's sake. And then plus e hat z times, well, the determinant of this would just be vx wy minus vy wx. And I believe this is actually supposed to be vz x and z. And yeah, so we could just distribute this negative sign. So this vector would just be e hat x vy wz minus vz wy plus e hat y vx wz minus vz wx plus e hat z vx wy, wait, I think this is, yeah, vx wy minus vy wx. And there we have it. This is our vector, which is defined using the determinant derivation of the cross product. And there is also another, which requires summing and all that, which when we'll also be using the Levi-Civita symbol. So let's get into that, because this requires a lot of memorization and putting everything together and all that. So we're gonna keep the v cross w. So let's talk about the Levi-Civita symbol. So it's going to be I, J, K is going to be equal to basically, so 1 if cyclic, -1 if anti-cyclic, and 0 else. So basically, like, well, what exactly do we mean by cyclic or anti-cyclic? So cyclic would just mean like if we were to take the order of say I, j, and k, it would just be 1, 2, 3, uh, 1, 1, 2, 3, and 2, 3, 1, and 3, 1, 2. So basically, you can notice that if you were to start at 1, it would go up to 2, then to 3. And then if we want to start at 1 from here, it would be from then 2 to 3, and then 1, then 2 to 3. And anti-cyclic would just be, well, 2, 1, 3, 3, 2, 1, and 2, 3, no, 2, 3, 1. No, that's not right, not 2, 3, 1. Oh crap, I forgot. And yeah, basically 3, 1, 2. So basically, like, what you notice in anti-cyclic is if you were to start at 3, then you go 2, 1, and then 3, 2, 1. And well, I seem to have forgotten the last value, but which takes the order of 3, 2, 1. And then it would just be, yes, I remember. So it's basically 2, 1, 3, 3, 2, 1, 1, 3, 2. And this all yields a negative not 1. This all yields a positive 1. And basically, else usually means repeated sum. So 1, 1, 2, 1, 2, 2, 3, 1, 1, etc. And that just yields 0. And honestly, the Levi-Civita symbol of deriving the cross product is actually probably much easier to do than, say, the determinant matrix. Simply because that you have to remember to multiply everything, and like you have to do a lot of memorization, which for most people is not always easy. So anyway, how can we use this fact to prove the cross product? So we can do this component by component. So V cross W sub I, where I could just be equal to 1, 2, or 3, or just X, Y, or Z. It would just be equal to the sum over J and K, I believe. And so let's just ignore the sum. So equal to this sum over J and K, VJ, WK, E, no, not E, epsilon IJK. So like we can, so in this case when we are summing over J and K, well, let's say if we wanted to do this quickly and efficiently, well, if we wanted to do this quickly and efficiently, we can always ignore for, well, J equals K. We can ignore for J equals K. And so what if we wanted to find the X component? So V cross W sub X. Well, X will just be, in this case, the first dimension, which is equal to, well, sum over J and sum over K. VJWK, epsilon, well, in this case is 1JK. And well, the X components, well, since we're ignoring for J equals K, well, we can put, it would just gonna be V1, no, I believe, Vy, because, well, for J equals 2, which is just Y, Vy, W, Z, because when we yield J equals 2 and K equals 3, well, that just means that we get a positive 1. And then minus VZ WY, because in this case this is anti-cyclic. So basically, so our first part of the cross product going to be equal to VYWZ minus VZWY. Let's make that a better W. And it will just be. So what if we wanted to find this? So we found our x component, and next we're gonna find a y component, where we could easily derive the exact same way. Well, sum over j and sum over k, vj, wk, epsilon 2jk. So how will we make this one cyclic? Because it'll be much harder to do. Well, if we wanted to go in ascending order, well, that means j must be equal to 3. So, j is equal to z component. So making this positive will be vz, w, x, and then anti-cyclic. Well, you just switch the two around, and you would just get vx wz, and that is our y component. So I'm just going to put this here. And rub this out. And that finally, our final job is to find the z component. So v cross w z is equal to the sum over j and sum over k, vj wk, epsilon 3 jk. So if we wanted to make this cyclic again, well, that means j must start at 1 again, so that k equals 2. So this would just be vx wy minus, and then switching the two around, vy wx. And well, this is our final term for our cross product. So how can we put all of these together? Well, if you wanted to put all of these together, we can say that v cross w is equal to, well, what is the first one we want to look for? The x component, vy wz minus vz wy, all over e hat x. And next, it will be the y component, vz wx minus vx wz e hat y. And then plus, well, the final one, so vx wy minus vy wx times e hat z. And that is our cross product. So I hope you enjoyed watching that video and maybe got something out of it, because I would truly be thankful for you watching this video. And also, if you're willing to press that subscribe button. So I'll see you next video, and ciao.